Lecture number 4 about the polynuclear aromatic hydrocarbon subject, chapter number 2. So we start with the anthracene. Anthracene is a solid polycyclic aromatic hydrocarbon consisting of 3 fused benzene rings, these 3 cycles, and serve as a fundamental building block in organic chemistry. Also, it is an important unit for synthesis in organic chemistry. Can be prepares compound like dyes or some molecules that has special electrostatically properties, electronic properties. So there are 4 resonance structure for anthracene. This number 1, and this the second resonance structure, third and fourth. All of them, they are anthracene, resonance structure for the anthracene. We start with the synthesis, how we can prepare this compound. So the first method he showed here is the Friedkraft alkylation. Friedkraft alkylation. طبعا this it will be entered to the alkylation, and also this it will be entered to the alkylation. So this it will be as electrophile, and it will be substituted to this ortho position here, and this it will be also second electrophile, it will be substituted to this ortho position. So we have here carbon new bond. Also with this carbon we have also new bond. So it will be closed or bind two molecules together with two sides. So from here and from here to give us these molecules. These molecules enter to the aromatization with the decrease or remove the hydrogen atom to give us the anthracene. So the again step number 1 is called alkylation, but from the two sides. So to bind two molecules together, so it's called dimerization here. The reaction proceed via two successive electrophilic aromatic substitution. The carbocation from one benzyl chloride molecules attack the benzene ring of the second molecules. This happened twice, cross-linking on both ends, resulting in the formation of the central 6-member ring containing 2 methylenes. Bridge. The intermediates form is 9,10-dihydroanthracene. This compound is 9,10-dihydroanthracene. That meaning we have on the position number 10 and 9 or 10 we have hydrogen excess 2 hydrogen here. So reduce this hydrogen, remove this hydrogens here to give us the anthracene from the dihydrogenation, aromatization to give the aromatic system again. So the second method here to prepare this compound from benzene and phthalic anhydride. What we have here? We have a classical 3-step chemical synthesis of anthracene starting from the benzene and phthalic anhydride. This phthalic anhydride and this is the benzene. So we have here alkylation. We have here acylation. The Friedkraft acylation. The first reaction here, acylation with aluminum chloride. So when this give us electrophile, it will be open, and this side it will be carboxylic acid side, and this it will be the electrophile here when react with the AlCl3. So to produce the electrophile, and the electrophile it will be substituted on the benzene ring. This is step number one. About step number two here, what here we have cyclizations from this side, new carbon-carbon bond here, the intra-molecular cyclization, because the cyclization will be happened on the same molecules here. So we have ring closer. The sulfuric acid act as dehydrating agent and catalyze a second molecules. Okay, by using H2SO4, we remove OH with H here, remove H2O molecules to give us the anthraquinone, this anthraquinone. So Clemmensen, by using reduction here, Clemmensen reduction, the carbonyl group it will be convert to the anthracene, to the CH group here. Reduction طبعا by using zinc act as a reducing agent, stripping the two oxygen atom, the ketone group from the middle ring. It will be remove the carbonyl from this position, position number 9 and 10. The third method to prepare this compound, the anthracene, is Earps reaction. This is a pyrolytic method used to synthesize polycyclic aromatic hydrocarbons like anthracene. What is this method? If we look at here, pyrolysis. So if you look at this compound is orthomethyl benzenophenone, this orthomethyl, and this benzenophenone. Okay, benzophenone. يعني dial phenyl ketone, the second name if you want, dial phenyl ketone. مهم. So the reaction proceeds via pyrolysis, so which involves heating of compound to very high temperature, typically around 400 to 450 degrees. No catalyst is used here. So the reaction is often show and produce variety of طبعا byproducts, the anthracene. It is a special industrial method here. So to give us the anthracene from orthomethyl benzophenone, and this process at high temperature, it's called pyrolysis. So pyrolysis meaning is a chemical reaction process under high temperature, maybe with oxygen or without oxygen. Can be, both of them can be used. So this is the meaning for pyrolysis, is a term for this process. The fourth method to prepare the anthracene from the benzene and phthalic anhydride. So if you look this diene and this alkene, the dienophile here. So it is clear from this reaction is these aldehyde reaction here. So three-step chemical synthesis for producing anthracene, starting from 1,4, this 1,4 naphthaquinone, and 1,3 butadiene, this 1,3 butadiene. The first reaction is this aldehyde reaction, and then reduction. Reduction decrease the hydrogen atom here, and aromatization here. So step number 1, these are the cyclo addition here. So the dienophile, this is the compound, the dienophile, we say dienophile, act as dienophile, want diene, and this is the diene. So the double bond on the quinone ring is highly reactive because it's a flank by two strong electron withdrawing carbonyl. So this electron withdrawing and this electron withdrawing. So this is so active double bond here, double bond. Step number 2 is the oxidation and also reduction to give the aromatic system. Again, this intermediate products from the first step then oxidize to great fully conjugated aromatic system. The CrO3 remove hydrogen atom dehydrogenation process from a newly formed cyclohexene ring. Step number 3 here, the final step is serve reduction to remove the oxygen atom and yield the final polycyclic aromatic hydrocarbon. This to prepare the anthracene from the well for naphthoquinone three-step reaction. So the fifth method to prepare the anthracene, and we use it to prepare also the naphthalene. طبعا naphthalene substitute also and not substitute naphthalene is the Haworth method. So Haworth method again here. Look to the first reaction is acylation, and second one here is cyclization, and then reduction, Clemens reduction or another reduction to produce the aromaticity in the middle cycle to prepare the anthracene. Okay, I will don't put additional explanation because we explained the method before that. Okay, we explained this method and this in the preparation of the naphthalene, so I don't explain the method here again. So it is clearly for you acylation. Okay, acylation, and here we have cyclization here, intramolecular cyclization, and then reduction to produce the anthracene. Okay, so we have another method to prepare the anthracene here is by synthesis of 9-alkyl anthracene. Okay, but طبعا the same procedure by Haworth method. So we start also from the benzene and anhydride here to prepare. First step is acylation, and here it is reduction to convert the carbonyl group to CH2, and then cyclization. This is the cyclization. So because we want substitute naphthalene, so we have here additional step is the reaction with the green reagent. So if you want CH3, you'll be use CH3 MgBr. If you want مثلا CH2 CH3, you'll be use CH3 CH2 MgR. You have to change the R group here as you want it. So here the reactions of the carbonyl group with the green reagent. So we have addition on the across to the carbonyl group. So final step is dehydration to give you the 9-alkyl anthracene. You have to change the alkyl. If you want CH3, that meaning 9-methyl. If you want ethyl here, it will be 9-ethyl, 9-ethyl anthracene, 9-propyl anthracene, like that. So another method to prepare the anthracene is from the naphthalene via these other reaction. So first step, oxidation طبعا step with the K2Cr2O7 to give you this compound. So this compound again as this step exactly where is it here? Again 1,4 naphthalene, the same step here. Okay, these are the reaction with 1,3-butadiene. The same thing here. Good. These are the reaction. So also here we have dehydration and then a reduction again to remove the carbonyl group to prepare the anthracene. This method, we take 6 or 7 different methods here to prepare the anthracene compound. So we have to talk about the reactions of the anthracene. First reaction of the anthracene is these are the reactions. The anthracene, it will be as diene to react with the dienophile with anhydride compound. So the example here with malic anhydride, this is the malic anhydride. So the position 9 and 10 in the anthracene, they are active positions here. So the substitution, it will be happened on the addition of the alkene double bond, it will be happened between this two position. Okay. So what we have here, we have these other reactions. A power for 4 plus 2 cycloids addition here, 1 2 3 4, and this 2 4 plus 2 cycloid addition use organic chemistry to form 6-member ring. Okay, to form 6-member ring. Where is the 6-member ring? This 1 2 3 4 5 6 to give you 6 new cycle here. Okay. So the anthracene act as diene, this is the diene, and malic anhydride, it will be do as dienophile. So the second reactions also for the anthracene was the oxidation with the oxygen gas, reaction with the oxygen gas to give you anthracene epoxide. This epoxide, we know the epoxide compound ROOR. Here anthracene epoxide, that meaning we have here alkyl group, oxygen alkyl group. So what we have here, if we go to the explanation, so the reaction here with the oxygen gas to form anthracene epoxide, it is a product to be the basic, as I told you before, that is R oxygen R the endo-epoxide, especially at 910 endo-epoxide, not a simple epoxide. Okay, it is not cyclic epoxide here. The reaction is a classical example for 4x2 cycloadditions. Also known, these are the reaction here where oxygen act as dienophile. So this also is types of these other reaction, because the two oxygen atom here is oxygen double bond oxygen. So it is example for these other reaction. Halogenation with the Cl2 Br2, also it will be happened on position number 9 and 10. So if we want to reduce one hydrogen and one halogen, dehydrohalogenation, so this is the halogenation method. Both of them, it will be substituted with the halogen. This dehydrohalogenation here to remove hydrogen and halogen here. Okay, so we have here addition reaction it will be happen at position number 9 and 10, addition of the halogen. So the second reaction here, the molecule will be lost the hydrogen halide molecules HX, yani minus HX, dehydrohalogenation. This can be happened with presence of weak base by using any base. Just add base here to remove edge X, to give you dehydrohalogenation process. Another reactions for the anthracene is the oxidation of anthracene. The oxidation of anthracene to form 9 to 10 anthraquinone is the reaction here. This reaction is a classical example of how polycyclic aromatic hydrocarbon behave when exposed with oxidizing agent. So the anthracene, it will be react with dilute HNO3, okay, to give you 9,10 anthraquinone, and this specific case diluted nitric acid here act as oxidizing agent, it will be specifically targeting the most reactive side on the molecule. Where is the most reactive side on the molecule? This most reactive side on the molecule, 9 and 10. This and this. This and this. Two oxygen atoms here are added, and the central ring lost the full aromatic system for the double bond characters to become a quinone. This is the quinone. Anthraquinone, this quinone. The final product is 9,10 anthraquinones. This 9,10 anthraquinone. The reaction it will be with K2Cr2O7 oxidizing agent here. Reduction of the anthracene. So specific organic reactions known as Berge reduction here apply to anthracene to produce 9,10 dihydroanthracene. This 9-hydrogen. So these reactions, Berge reductions, reaction with the sodium and heating. Okay, with the sodium, with heat the reaction. So yeah, reflex the reaction in ethanol. طبعا, of course, the boiling point of the ethanol is 78, so the heating here it will be until to the 78, reflexing here to give you this product. The third type of the polyaromatic hydrocarbon here is the phenanethrin. Also, phenanethrin consists of 3 cycles here, but not linear like anthracene. So the phenanethrin is the polycyclic aromatic hydrocarbon consisting of 3 fused benzene ring. Unlike anthracene, where the rings are arranged in straight lines, phenanethrins it will be angular structure. Angular, we have angle here, زاوية. It is not straight, not linear. So when start numbering here, to put numbers for the carbon atom, we start from this cycle, not from the middle, one of them, but not from this side. Okay, not from this side. Don't say 1 2 3, 1 2 3 4 like that. Okay, no, it will be 1 2 3 4 from the sides that has 2 carbon atoms from the neighboring cycle. Okay, 1 2 3 4. This without number. This is bridged carbons. So 5 6 7 8. Not 9, 9, 10, like that, 9, 10. Okay, this is the position here. So the resonance structure for the anthracene, this number 1, 2, 3, 4, 5 resonance structure we have here. All of them, they are anthracene. They are phenanethrin. We talked about the phenanethrin here. They are phenanethrin. So all of them, they are phenanethrin. 1 2 3 4 5. Um, Again, don't forget the numbering. It will be for the phenylethrine, it will be started from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Um what we have it here, the bridged, how many bridged atom, carbon atom we have? 1, 2, 3, 4. 4 carbons atoms. They are bridged in the phenylethrine compound. So the preparation of phenylephrine here, the first method is the Haworth synthesis. Also, we have acylation, as we said before, acylation with the succinic anhydride, with the anhydride compound, this acylation. And we have reduction, reducing the carbonyl group, okay, and then cyclization, intramolecular cyclization, and then another Clemmensen reduction here. So finally we have aromatization to produce the aromatic system in this cycle. 1, 2, 3, 4, 5 multi-step reactions to prepare the phenylephrine compound. This is not substituted phenylephrine. So if we want one here, one alkyl phenylephrine, also from this step, look, from this step, from here, this, it will be react with the Grignard reagent. This, it will be react with the Grignard reagent. Methyl Mg, that means CH3 here, Mgi. So it will be give you Cahol, and then the Cahol enter to the elimination, and then oxidation, also reducing the hydrogen, aromatization to give the aromatic system here. So if I want substituted for the phenylephrine, I will start from the naphthalene also to this step, and this step it will be react with the Grignard reagent to add a methyl group here in this position, and this step. Preparation 2-alkyl phenylephrine here. So look to the 2-alkyl phenylephrine here. We use substituted anhydride. So this it will be open from this side, to give you this intermediate product. It's carboxylic acid. We have carbon here. Enter to the Clemmensen reduction to reduce the carbon to the CH2, and then anthracyclization, finally reducing the carbonyl group to the CH2, and aromatization to give two substituted phenylephrine, also by Haworth synthesis. This also Haworth synthesis. Here the pusher synthesis, or like that, show the sure synthesis, this German word, pusher synthesis, or maybe it will be refers as sure synthesis. The primary objective of the sure reactions is to form a new carbon-carbon new bond between aromatic rings, effectively linking them to create larger ridged polycyclic structure, this here. So what we have here, we have carbon-carbon new bond in this area between the aldehyde and the CH2 group. This we have here a carbon-carbon new bond with aceto acetic anhydride as solvent, and then reduction of the NO2 nitro group to the amino group. So finally convert the amino group to the diazonium salt, and then finally diazonium salt here, the carbon, it will be cyclization in this position to give you the phenanethrin. So we have here new reactions. We have here new reactions for you. We have here cyclization. So it will be like that. This procedure. First reactions, as we grade or I don't explain the mechanism in this lecture. It is not related with you now. If I want to explain the mechanism for this and this and this, it will be long subject for you. So we have here new carbon bond here because we have this carbon and this carbon between the aldehyde and this CH2. It will be give us carbon double bond carbon. Reduction, reducing the nitro group to the amino group, and then convert the amino group to the diazonium salts, and diazonium it will be entered to the anthracyclization with the second cycle to give us carbon-carbon new bond here. This is the procedure, reaction with copper. Okay, reaction with copper. Perkin, so the first reaction here, if we go to the details of this scheme here, the first reaction is Perkin condensation. This Perkin condensation between the first step is Perkin condensation between orthonitrophenylaldehyde here and sodium phenyl acetate in the presence of acetic acid. Okay, this is alpha acetic hydrogen, and this as aldehyde. This Perkin condensation. I don't explain the mechanism. Okay, without mechanism. So why condensation here? Because you know the condensation is not just coupling and then remove H2O molecules. Coupling, remove H2O molecules to give you the carbon double bond carbon here. The second one here, reduction of the nitro group. طبعا using Clemensing type condition, zinc AgHCl. Clemenson's because we used zinc AgHCl acidic condition, and finally diazotization here, the amino group it will be converted to the diazonium salts, and finally cyclizations is and decarboxylation here, cyclization and remove the CO2 edge. So the final step, treatment with diazonium salt with copper power here. طبعا the mechanism copper catalyze the loss of the nitrogen gas here, create a final phenyl radical. The radicals then attack the adjacent aromatic ring intramolecular cyclization. With decarboxylation, it is clear for you here is طبعا the carboxylic acid group it will be lost as the CO2 gas, carbon dioxide gas, decarboxylation. This about here, decarboxylation, remove the CO2H, cyclization and decarboxylation, the reactions with the copper. So the reactions of phenanethrin, I don't give you the reactions alone. Here I don't go to the further details. But if you look here, phenanethrin, it will be react with Br2 bromination. These two position here, they so active to the electrophile here. So at room temperature, the bromination will be added to the carbon-carbon double bond bromination. If we want to add hydrogen, a reduction here, it will be converted to the 9,10-dihydrophenanethrin reaction with the sodium and alcohols here, and alcohols, hexanol, ethanol, this one of them can be used. The ethanol is source for the hydrogen. sorry يعني alcohols, it will be a source for the hydrogen. The reactions also here at reflex, just one bromination will be happened here. The reactions with Cr2 or with CrO3 oxidizing reagent oxidation process, this oxidation process, reactions with ozone gas and two-step reactions and H2O to give you this compound. This compound can be also converted to the aldehyde group to the carboxylic acid group with the reaction with KMnO4. These types of the phenylethrine reactions can be and there is طبعا of course there are further reactions for the phenylethrine, but this is just to give you idea about some different reaction here. It is just like reduction, oxidation, halogenation, and so like that. So this chapter it's finished until here, and thank you for listening. See you. Good luck.